So now that we've learned the Beltrami identity, we have a shortcut for solving the Brachistochrone problem. That is, we start at A, we're trying to get to B in the shortest time possible. If we take a straight line, which is the shortest distance, then we might go a bit slower than if we start a little steeper and go a bit longer. So the total time taken we worked out was this integral, and this function here, you'll note, does not depend on x, and therefore we can use the Beltrami identity. Now we could go through the details of calculating this, and I might just remind you that when you take the derivative with respect to y dot, you assume y is just a constant. But when you do that, you just basically end up with a dE, a first order dE this time. This was originally posed by Bernoulli and solved by Bernoulli, and Bernoulli was clever enough to develop calculus of variations specifically to solve this problem, and so it's unsurprising that he's a pretty smart guy. He came up with a parametrized solution, which just happened to be the very fact that the solution is best written in a parametrized fashion is a clue to us that it's hard to solve. And sometimes in your careers you might end up having to solve a hard DE, but if it's really hard, you look it up, or possibly do it numerically, or ask someone who specializes in such things. But there's the solution, and we've solved that problem. The answer, by the way, is a cycloid, which is the shape that a wheel makes. If you have a wheel with an axle and you put an X there and you just wheel the wheel along, then this thing makes a kind of shape like this as it goes around. If you turn that upside down, that's the shape that this should be. And that's indeed the shape that they make certain kinds of roller coasters to kind of give you a good feel of speed as you zip around.